So today I'm going to talk about nanomaterials discovery as a tool for innovation. I should introduce myself. I'm Kyle Cordova. I work here in Amman, Jordan, where I am helping to build the research capacity of the Royal Scientific Society. So when we think about discovering nanomaterials, we first have to understand how do we actually construct materials. So a basic concept for the design and engineering materials is that all chemical structures are entirely composed of joints and links. And so what I'm showing you here is a drawing by the artist Escher, but it's a perfect representation of a chemical structure. So here you see a joint, and here you see a joint, and they're connected together by links. And that continues on in a periodic fashion in 3 dimensions. And so if we understand that all chemical structures are composed of joints and links, the question then becomes, well, how do we design those joints and those links? And so in order to get predictable structure and composition, there's really only 2 basic requirements, and that's that your building blocks must have directionality. So in the case here, the joint is a building block, and it can be connected upwards, to the back, to the side, over here, and to the left. And that's what I mean by directionality. Now, the second basic requirement is that it has to have a well-defined coordination geometry. So again, I'll go back to the Escher drawing and show you that I have a cube that can be connected in 6 different ways. So again, chemical structures are always made up of joints and links. In order to define or to design those joints and links, your molecular building blocks have to have directionality and geometry. So in my field, which is called reticular chemistry, we have a class of nanomaterials called metal organic frameworks. There's 2 different building blocks. The first one is metals, which is the metal and metal organic framework, Moths. And we find in chemistry that there is a diverse library of metal clusters that meet all of the criteria that I just outlined. They're well-defined and they're directional. So here I'm kind of showing a sample of these metal clusters. They come in all shapes and sizes. Here you see a rod, here you see a square or a trigonal prism or a triangle or this octanuclear cluster. So again, these are well-defined, they're directional metal clusters. That's our first building block. Our second building block takes advantage of organic chemistry. And in this case, again, we have well-defined directional structures that we can actually synthesize in the lab. And these are kind of generic representations of the organic linkers. But again, you can get a sense that the directionality and the geometry are well-defined. Here I have a ditopic, meaning it can connect from 2 different ways. It's a linear line. Here I have tritopic, meaning it can connect 3 different ways. It's a triangle. When I go to a 4-connected organic linker, I can have different shapes now. I can have a rectangle, I can have a square, or I can have a tetrahedron, and so on, all the way up to, say, dodecatopic organic linkers. So my 2 molecular building blocks in metal organic frameworks are metals and organic linkers. But how do we actually design these things? How does it play out in the laboratory? Well, first we actually we think about what structure we want to make, and we reduce that down to its basic elements. So that's what I'm showing here on the left. If I just want to make a cubic nanomaterial, a cubic moth, I have to draw a cube, and then I start to identify those the 2 primary things that make up a chemical structure: the joint and the links. So here the ball is the joint, and the links is this orangish rod. Now, when I look at the joint, I see it's connected to 6 different things. With just a basic understanding of geometry, you know that a shape that has 6 connecting points is an octahedron. So I can replace this ball with an octahedron, and I know that the balls are connected by a linear line, so all I need to replace this rod with is just a linear line. And now here's when the chemical intuition starts to play a factor. I know that a metal cluster called zinc acetate is in the shape of a octahedron, and I know an organic molecule, which is terephthalic acid, is a linear line. So then now I can start to target the use of zinc acetate for my metal cluster and terephthalic acid as my organic linker. When I link them together, then I can make this cube as you see right here. Now, why is this exciting? Because of this yellow ball. The yellow ball has no scientific meaning other than to just show you how much free space is inside of that structure. And that free space is where all of the fun happens. That's when we're able to use these materials for certain applications. So what I hope to have shown you in these first several slides is that we are able to design rationally porous frameworks or porous nanomaterials. And it gets a little more exciting. So if I want to make, I keep showing you the cube because it's a very simple example, but we can get more complicated. Again, I have two different molecular building units. And if I have a linear building unit number 1 and a triangular building unit number 2, I can actually predict the end structure, which in this case is SRS. If I have a tetrahedron for one of the building unit and a square, then I'm going to get this PTS, which is the same structure as platinum sulfide. I can start to get a little more complicated with the building units in terms of their shape. If I have an octahedron for one building unit and a square, then I get this SOC structure. And for all of those places that you see just a simple line right here, those are the areas that are yet to be explored, meaning we can predict what the structure will be based on geometric principles, but they've never been realized or synthesized in the actual lab. And finally, I can get really, really complicated with cube octahedrons or icosahedrons or truncated octahedrons. And again, if I just match them up with the shape, the well-defined shape and directional other building unit, then I can predict these structures. Why is that exciting? Because we end up with molecules that look like this. This is Moth 200. And in Moth 200, you see all of this free space inside. And this free space is not blocked off by any walls. So if I'm a guest molecule coming into the structure, then I'm able to move in from here all the way over here. And that allows me to have the ability to design the interior of the actual structure for specific purposes. But what is also exciting, because of all this free space, all of this pores without walls, is that I have ultra high surface area. And so just to give you an example, if I have the size of a half dinar of moth, basically 1 gram, 1 tablespoon, if I unraveled that on the molecular level, I would have the same surface area as a soccer field. Okay, so just 1 gram, if I was able to unravel that, I have that same surface area. So that allows me a lot of space to explore specific uses of these materials. So in the case of the moth I showed you here, Moth 200, it has a surface area of 10,000 square meters per gram. That's very, very exciting. So I keep alluding to the fact that we have a lot of space inside of these materials to explore for applications. And in today's talk, I wanted to focus the applications of these moths, these metal organic frameworks, on 4 different molecules, because I think these molecules are really changing the world. The first 2 that I show here on the left is methane, which is the main component in natural gas. It's a fuel source. It's cleaner than petroleum. It's not absolutely clean, but it's better than what we currently put into our cars. And then hydrogen, which is the cleanest fuel, meaning when you burn it, it doesn't release any carbon dioxide or any other greenhouse gases that contribute to global warming. So I'll talk about how moths are applied in these cases briefly. I'll talk about carbon dioxide, which we all know is a greenhouse gas and it's detrimental to our planet. So I'll talk about how moths are applied in solving this problem. And then I'll end with kind of the hot topic in the field of reticular chemistry and moths is water, and how I think in the Arab world, you guys know this a lot better than the rest, is that fresh, clean water is needed. And we've found a way to be innovative in addressing this problem. So first, let me show you a short little animation about, so it will help you visualize how moths interact with gas molecules such as methane, hydrogen, carbon dioxide, or water vapor. And so here you see nanoparticles of moths. They have a well-defined morphology. In this case, they're cubic, but they don't have to be cubic. So we're going to come up into one specific nanoparticle. We'll call it Moth 5. And as it rotates, you start to see all of that free space inside. And gas is starting to accumulate around it. And because we're able to tailor the interior, we can attract the gas molecules inside of the pores so that they stay closer together than if the moth was not there. If you remember, gas molecules like to bounce around and they don't like to be compressed without high pressure. But in the case of moths, because of the attractive forces, we can pack gas molecules closer together. And so there you see these blue little species are the gas molecules stuck inside. So that's how these moths really function. So in the first case, for methane and for hydrogen, this is a moth made by a Palestinian-American professor named Omar Farha at Northwestern University. It's NU100. If I take a gas cylinder and I pack this gas cylinder full of NU100, and then I add natural gas, whether that's methane or I add hydrogen gas, I can store the equivalent in this one cylinder full of moth as 10 empty cylinders. Okay, that's very, very exciting from the standpoint of now I don't need these excessive pressures in order to compress the gas inside, which makes it dangerous, makes it a ticking time bomb, and I can start to think of cars that use the fuel tank full of moth in order to store larger quantities of fuel in order to drive longer distances. That's very, very exciting. It was so exciting that in I think 2013, BASF, which is the largest chemical company in the world, made a prototype vehicle with a moth-based fuel tank. So in that car, it was driven by natural gas. They were able to extend the driving range by some 200 kilometers per fill-up. And now this is kind of just a side little anecdote. For all of those people who are excited about translating their research from the lab into the market, this is a cautionary tale that don't get too excited because there's forces at play that are outside of your control. And what I mean by that is that in 2013, BASF was about to roll these cars, this fleet of vans, onto the market in Europe. But right as they were set to release these cars, the oil prices dropped, and therefore natural gas was not economically feasible anymore. And so they had to shelve these. And to this day, it's still not economically feasible to roll these out. So although there was a great innovation and the product was ready to go, sometimes things are out of your control. So that's for methane and for hydrogen. In terms of carbon dioxide, moths really play a role in each step of the carbon cycle. I think we all know that petroleum comes out of the ground, it's refined, and then it's used as gasoline in cars. And in the US alone, 17 tons of CO2 is generated per capita. And so it's from that exhaust of burning these fossil fuels that carbon dioxide goes into the atmosphere. And I don't need to tell you about all of the implications that creates. But when that exhaust happens, it's a mixture of different gases. It's not just carbon dioxide. There's nitrogen, there's oxygen, there's water vapor, there's SOx, there's NOx. There's a lot of different contaminants. But the most important one to trap before it gets into the atmosphere is carbon dioxide. So we're able to design moth structures that are functionalized to selectively capture the carbon dioxide and allow the other gas molecules to go into the atmosphere. Now, that's exciting. We stopped CO2 from going into the atmosphere, but what do we do with the CO2 now that we have captured it? Well, there's two different ways. Number one, you can store it in a different moth. So this is Moth 200. It has a very, very high surface area, and you can store large quantities of CO2. You can store it, and then you can transport it, and then eventually inject it down into the ground. That's something called sequestration. Or what's getting a lot of attention these days is the reuse or conversion of carbon dioxide to more value-added commodities. So you can do enhanced oil recovery processes, or you can convert them to value-added chemicals like urea, oxalate, or olefins, or even make new plastics out of them like polycarbonate. So you're taking CO2 and making a new plastic, or creating a clean fuel like methanol. So MOFs, metal organic frameworks, reticular nanomaterials, are applied to each step: capture, storage and transport, and then conversion. MOFs are also catalysts for this process. And so one of the exciting new avenues of research for CO2 conversion by MOFs is photocatalysis. So in this case, because the MOFs, all of the different molecular building units can be functionalized and changed and tailored almost at will, we can really design the ultimate catalyst to use sunlight as a source of energy, which then reduces carbon dioxide into to other chemicals like methanol, methane, which is also formic acid, acetic acid, etc. So this is very, very exciting. We reported this back in 2 years ago in Nature Materials, and I encourage you to read this article. So that's CO2. The final one is water, and I think we're all aware of all of the different techniques and tools that can be used and have high potential for generating clean drinking water, whether that's water treatment, water purification, water desalination. But with Moths, we were a little bit creative, and we started to look, because Moths are able to selectively capture specific gas molecules based on how we design these frameworks. We started to think about water and all of the water that is present in the air at any one time, even in the desert climates. So here I'm showing relative humidity profiles versus the time of the year, the month of the year. And if we're able to absorb or capture water just from humidity in the air and release it within this range right here, and we can use the sunlight as a source of heat to release the water, then we potentially can create a water harvester. Now that, if you've seen the Star Wars, I think I forget which episode it was in, but there's a moisture harvesting farm, and so it's the stuff of science fiction. But over the last few years, we've made considerable progress, and I'm about to tell you about that now. So the first prototype that we invented at Berkeley, when I was at Berkeley, was what I'm showing you here. So here we have a box within a box. This box contains a metal organic framework, a specific one that is designed to capture water directly from the air. And at night, when the humidity is a little bit higher, it doesn't need to be 60, 70%. It could be 15%. It could be as low as 10% or 5%. It's higher than during the day. At night, when the humidity is relatively higher and the temperature is cooler, we open the box so that the moth is exposed to the air. Now, the moth, because it's designed in a specific way, captures that water. And then during the day, we close the box. The sun comes out, the temperature rises. We take advantage of that heat, and that heats up the box. That drives the water to be released from the moth. It comes to the box, condenses into actual droplets. Heat it flows out, and then water is actually collected on the ground. So now we can actually, as of 2018, we can conclusively state that we can harvest clean drinking water directly from the air. And I do want to mention that this was not done in an area or a city with high humidity. This was done out in the Arizona desert, which is very, very similar to the climate here in Amman, Jordan. Now that's exciting, but the limitation here is that we're focused on a day and a night cycle. So actually harvesting water takes a long time. So it would be much more exciting to develop an active water harvesting device. And so that's what we set out to do. And here it's the same exact principle. At night, water was captured. During the day, water is released. Water is captured. Water is released. Water is captured. Water is released. But this time we can do multiple cycles at night, not just open it up and wait for the water to be captured, but we can do now 1, 2, 3, 4, 5, 6 different cycles every single night. And that allows us to capture, condense, and deliver more drinking water. So again, what happens is that dry air with a little bit of relative humidity, just a couple water molecules in there, is passed through using a fan into moth cartridges where it's captured selectively. Then using a heating source, you can drive out the water to a condenser where it condenses down into liquid water, and then it goes back to its original state. It's very, very exciting because now we can do multiple cycles per day. It's active. If we don't need water, we don't need to run it, or we can slow down the number of cycles we do if we've already have enough water, etc. Now, this is what it looks like. Again, it's a laboratory prototype built in the lab of Omar Yagi at UC Berkeley. It's completely off the grid, so you don't need any electricity. It just uses a solar panel. You have batteries to store some of the energy that is needed to heat up the device. This is where the moth is held. There's a fan on the back, blows it through, and then you use heat in order to release the water, and this is where it's condensed. And here you can see there's a tube running down, and water is actually being collected. And now this is pure water directly from the air. Now, the number one question I get is, can I just drink this? Well, you can't drink this straight away because it's deionized water. You would just need to add a little packet of some minerals in order to get the type of water that you're used to drinking, which is a couple cents. So that's not the big issue. Today I just talked about carbon dioxide, water, hydrogen, and methane, but moths are applied to a lot of different areas. They're very good sensors. They're very good proton conductors for proton exchange membrane fuel cells. They're good electrical energy storage devices like supercapacitors, similar to maybe not on the level as Dr. Sonia was describing with graphene, but there's promise there. They're a big burgeoning field is drug carriers, so you can load that interior with drug molecules in order to have targeted drug delivery. And again, a lot of stuff with gas storage, gas separation, purification. So I encourage you to read about them if you're interested in this type of nanomaterials. Finally, my last two slides. It might sound a little daunting, but it's actually quite simple. I'm showing you here 3 different students. They're high school students. To make these materials, it's just simply about getting a metal salt and an organic linker, putting them together, putting them in the oven. It's like baking, and out comes these beautiful nanoparticles. The chemistry really is so easy that even high school students can make new moth materials, not just repeat old moth recipes, but they can make new moth materials. So I encourage you to don't be shy about learning more about these. Finally, I'm here in Amman, Jordan, and I think a lot of the students in the audience are in Jordan. I'm at the Royal Scientific Society. We're currently in the process of building a new research center, which we're calling the Reticular Foundry. That's why I'm here, shown right here, where we are pursuing this type of research and also giving a lot of opportunities to emerging scholars like those that are listening today. There's a lot of research opportunities, so if you're interested, come join us and give me an email. Send me an email if you're interested. So thank you very much. I hope I didn't go over my time. I tried to go quickly. Yes. Thank you.